Dear students, we have discussed the resonant vibrations of a string clamp at two ends. Now in this section, we are going to discuss the oscillations of a rod clamp at a point on its length. Let us learn vibrations of a clamp rod. Now let us take a rod of length L and clamp at the middle point of the rod. Right? You can observe in this diagram, this metal rod is having length L and it is clamped or fixed at the middle point O, and P point and Q point are free. Okay, let us do one thing. Let us gently hit the rod at one of its ends, either P or Q. Let us hit the rod at point P. What will happen? Rod will start vibrating, right? There will be natural oscillation of the rod. Let us consider this rod start oscillating with the least frequency. And in case of the natural oscillation, where rod oscillate with the least frequency, and in case of the least frequency, there will be the maximum wavelength, because we have the formula wave velocity equal to frequency multiplied by wavelength. Wave velocity is constant in given medium. That means the wavelength is inversely proportional to the frequency. That means if frequency is least, wavelength will be maximum. So this type of the oscillation is called the fundamental mode of oscillation or fundamental tone. And waveform will be like this. Because this point O is a fixed point and fixed point is always node. So O will be the node and this P and Q both point are free point. So this will be the antinode and this is also antinode. And this least type of wave will be like this. So let us do one thing. Let us make this diagram to the next page like this. Okay. We know length of one loop is equal to lambda by 2, because in any one wave there are two loops and these two loops make one wavelength, that is length equal to lambda. Two loops, length equal to lambda. That means one loop should have the length equal to lambda by 2. And we can observe on the left side, this is the half loop and this is another half loop. That means this length of the loop should be equal to lambda by 4 and this is also lambda by 4. So lambda by 4 plus lambda by 4, that is equal to lambda by 2. And this lambda by 2 is nothing but L. That means we can write L equal to lambda by 2. That means we can write the wavelength of this wave form in this rod, that is lambda equal to 2L. Let this equation is 1, right? Now let us define the fundamental frequency. As we discussed, we have the formula wave velocity equal to frequency multiplied by wavelength. That means frequency equal to wave velocity divided by wavelength. So let us find the frequency of the fundamental oscillation of this rod, which is clamped at the middle. We can write N naught. Let us assign this frequency as N naught. So we can write N naught equal to V divided by lambda. And V is the velocity of the wave in this rod. This is a solid medium. This rod is having the Young's modulus, that is the modulus of elasticity, as Y. Let the density of this rod is rho. That is a density of the material of the rod. That means this velocity, that is the wave velocity, can be written as under root Y divided by rho. And this lambda is equal to 2L. That means we can now write the expression for the fundamental tone or fundamental mode of vibration. That is equal to 1 divided by 2L multiplied by under root Y divided by rho. This is the fundamental frequency. Okay. Now let us think about the next higher frequency at which the rod vibrate. We know for the next higher frequency, as frequency increases, the wavelength decreases. So for the next higher frequency, we can say this wavelength will decrease. If this wavelength decreases for the next type of the oscillation, there should be node in between the antinode and node. That means there should be one more node between point O and P. So if there is a node between this point and this point, so let us assign arbitrary position of a node on this rod here and here. So let us make the wave. You know, one loop length is length between two successive node to node. So there will be one loop and here should be half loop. So the waveform in this case should be like this. That is the one loop here, and this is a half loop, and this is another half loop. As we discussed, this half loop should be equal to lambda by 4, and this is also lambda by 4. And this length, that is the length of the one loop, that should be equal to lambda by 2, and this is also lambda by 2. That means lambda by 4 plus lambda by 2 plus lambda by 2 plus lambda by 4. Lambda by 2 plus lambda by 2 lambda, and lambda by 4 plus lambda by 4 equal to lambda by 2. That means lambda plus lambda by 2. That means this is equal to 3 lambda by 2. And this 3 lambda by 2 is nothing but length of the rod. So we can define the wavelength of the waveform in the rod by the relation L equal to 3 lambda by 2, and this lambda is equal to 2L divided by 3. This is the wavelength, right? Now oscillation frequency. We will use the same procedure for calculating the oscillation frequency in this case also. This is equal to, let us assign this frequency as N1. So N1 should be equal to V divided by lambda. V is again wave velocity. This wave velocity will be constant in the rod for any type of oscillation. So this is again equal to under root y divided by rho, and this lambda equal to 2L divided by 3. So we can write here this equal to 3 divided by 2L under root y divided by rho. We can observe here, in case of the fundamental tone or fundamental mode of oscillation or frequency, this is n not equal to 1 divided by 2L under root y divided by rho, and this n1 is equal to 3 divided by 2L under root y divided by rho. This is 3 times the fundamental frequency. So here we can write this equal to 3 multiplied by n naught. Okay, this frequency is called the first overtone or first overtone frequency, and here it is term 3. So this is called the third harmonic frequency. Now let us consider next higher frequency. So let us make the diagram again, right? We can observe here, this is a node, this is antinode, this is another antinode. For next higher frequency, what will happen? The wavelength will again decrease. So in the previous case, we have made one more node. So for the next higher frequency, for the less wavelength, we should have the two nodes on the either side of the clamp section. So let us make the wave like this, and node, node, and this is also node, node. So this will be the mode of oscillation for the next higher frequency. And here we can observe this length is lambda by 4. This is lambda by 2, lambda by 2, lambda by 2, lambda by 2, and lambda by 4. So let us write these length. Okay. Now if we add this, this is lambda by 2, lambda by 2, lambda. This is lambda by 2, lambda by 2 is again lambda. So this is 2 lambda, and this is lambda by 4 plus lambda by 4 is lambda by 2. So 2 lambda plus lambda by 2. So it is equal to 5 lambda by 2. So for wavelength for this type of oscillation, this L is equal to 5 lambda divided by 2. So we can write lambda equal to 2L divided by 5. So we got the wavelength of oscillation for this type of frequency. Again, we can use the same procedure for the writing frequency term. Let us assign this frequency as N2. So N2 equal to V divided by lambda, and V is constant, that is under root y divided by rho, and this lambda equal to 2L divided by 5. That means this frequency is equal to 5 divided by 2L under root y divided by rho. So here we can observe this frequency is 5 times the natural frequency. And this type of the oscillation is called the second overtone frequency or fifth. There is multiplication of 5s. That's why it is called the fifth harmonic frequency. Okay, so let us write these three terms all together. So let us make this first is the fundamental tone of vibration or fundamental tone or first harmony. And here n not equal to 1 divided by 2L under root y divided by rho. And in case of the next oscillation, we have one node and one node on either side of the fixed end like this, right? And here in this case is frequency is called the first overtone frequency or third harmonic frequency. And here n1 equal to 3 divided by 2L under root y divided by rho, that is equal to 3 times n0. And for the second overtone we have this type of the diagram, and in this case the frequency n2 is equal to 5 divided by 2L under root y divided by rho. This is 5 times of the natural frequency. Okay, so here we can observe the ratio of the frequency of oscillation, ratio of the natural frequency of oscillation is odd. 1:3:5. Okay, so up to this point we analyze fundamental tone, first overtone, second overtone, and in similar fashion we can analyze next higher frequencies. Now let us analyze the same problem by one more approach. Let us draw the diagram again. You can observe here in this diagram the middle point is clamp, that is a fixed end, and this is free. So this is node and this is antinode, and similar case for the right hand side part also. We can observe this is having the dissimilar end condition. Dissimilar end condition means one end is having the node, other end is having the antinode, or if one end is having the antinode, other will have the node. So this is the dissimilar end condition. So if we plot the cases of the higher frequencies, everywhere you can observe this is dissimilar end condition. This final point, that is P point, end of the rod is antinode and this is node, and similar for the next frequency. Now you analyze this part, that is PO section of the rod. In this section you can observe this section is having the half loop, right? And this section is having the one complete and one half loop. That means this is 3/2 loops. And here you can observe for the higher frequency, this is having the 1 and 1, 2 complete loop and half loop, that is a 5/2 loops, right? It means if we have the dissimilar end condition, we can generalize the case. We can say this type of the situation, that is a dissimilar end condition either on this side or this side, have the odd number divided by 2 loops. Or in general we can say we will have the 2n-1 divided by 2 loops, right? And we know the length of the one loop is λ/2. That means for this part of the length, this length is L/2, and this section always have the 2n-1 divided by 2 loops, and one loop is having the length λ/2. That means the total length, that is L/2, should be equal to 2n-1 divided by 2 multiplied by λ/2, right? Now we can find the value of lambda. Lambda, you can observe 2 and 2 will get cancelled. That means lambda equal to 2L divided by 2n-1, right? Now we can write the frequency. Frequency equal to wave velocity divided by lambda. Now we know the wave velocity for the rod under root y divided by rho. So we can substitute the value of v for the wave velocity, and for the lambda we can write 2L divided by 2n-1, right? So let us write this lambda only, this one. So this frequency term is now 2n minus 1 divided by 2l multiplied by v, and v is equal to under root y divided by rho. Now let us write this frequency, that's the general expression for the frequency, to the next page here. And here if we substitute this n is an integer, if we substitute n equal to 1, we have the least frequency, that is called the fundamental frequency. Fundamental frequency, let us write f naught. So f naught equal to 2 minus 1, that is 1 divided by 2l multiplied by under root y divided by rho. This is the fundamental tone or first harmony. Now let us move to the next case. Let us substitute n equal to 2 in this equation. This n equal to 2. Let us write this f2. f2 equal to 3 divided by 2l under root y divided by rho. This is the next frequency after fundamental frequency. This frequency is called the first overtone frequency or third harmony. In similar fashion, we can calculate the next frequency for the n equal to 3. So let us substitute n equal to 3 in this equation. If we substitute n equal to 3, that is a 6 minus 1, that is 5 divided by 2l, and 5 divided by 2l multiplied by y divided by rho under root. And this is the second overtone frequency or fifth harmonic oscillation, right? So we can analyze any type of the situation from the end condition criteria, right? This is easier way to remember the frequencies and higher frequencies. Now it is time to take one illustration for application of the concept. So let us take one illustration here. In this illustration, it is given a metal rod of length L equal to 100 centimeter is clamped at 2 points A and B. Say this point is A and this point is B, and this is clamped. The distance of each clamp from the nearer end is A equal to 30 centimeter. This is 30 centimeter. This is also 30 centimeter. That means this is 40 centimeter. Now it is given the density and Young's modulus of elasticity of the rod is, density is 900 kg per meter cube and Young's modulus is 144 gigapascal, right? Here we need to calculate the minimum and next higher frequency of natural longitudinal oscillation of the rod, right? So let us write the problem and make the diagram to the next page. This is the question and this is the problem, right? If we observe here, we can observe this is a free end, this is also the free end, and this is the fixed end, this is also the fixed end. Fixed end is always node, free end is always antinode. So this is antinode, node, and antinode and antinode, right? And we can, if we observe here, PQ section of the rod, here is node and here is also node. We can say this section, that is PQ section of the rod, is the similar end condition case. And in similar end condition case, rod oscillate with the integer number of the loop in the middle section, we can say, right? So we can say here the rod oscillate with the integer loops in this section. Let this integer number is small m. So let us call the number of the loops in this section is m loops. Now let us move to the next section, that is the end section. We can take left section or right section. Let us analyze the right section. If we observe this right section, this is the dissimilar end condition, and we know dissimilar end condition section always have number of the loops, that is the odd multiple divided by 2, that is 2n minus 1 divided by 2 loops. So this section always have the 2n minus 1 divided by 2 loops, and we know length of each loop is lambda by 2. So now let us relate lambda with the length of the section of the rod. Now let us calculate the value of small m and n. we know small m and n both should be integer. So let us do one thing. Let us place this diagram again to the next page like this. Okay. And let us first analyze this part, that is PQ part. As we know, this is having the similar end condition, and similar end condition is having the integer multiple of the loop, that is m loops, and each loop is having length lambda by 2. That means m multiplied by lambda by 2, that should be equal to L is the total length and this A is the hanging part, and here is also A. So this part is having length equal to L minus 2A, and this L minus 2A equal to m multiplied by lambda by 2. Now we can substitute the value of L, that is 100 centimeter, and A equal to 30, that is 100 minus 60, that is 40, and lambda by 2 multiplied by m equal to 40, that means m lambda equal to 80 centimeter. Let this equation number 1. Now let us analyze this section, that is section having the dissimilar end condition, and here we know number of the loops is 2n minus 1 divided by 2 loops, and we can do one thing. If we multiply this number with the lambda by 2, we will have the length of this section, that is equal to A, that is 30 centimeter. So we can write equation for this part, 2n minus 1 divided by 2 multiplied by lambda by 2 equal to small a, and small a, as we discussed, that is 30 centimeter. That means 2n minus 1 lambda equal to 120 centimeter. Let this equation number 2. Okay, so we got the two equations now for the middle part as well as left part. Okay, now we can calculate the value of small m and n. We can divide equation number 1 with equation number 2. So let us divide equation number 1 with equation number 2. So lambda will get cancelled. This value on the left hand side should be equal to m divided by 2n minus 1, that is equal to 80 divided by 120, and 80 divided by 120 equal to 2 by 3. So let us write this equation number, equation number 3. Okay, and here we are interested to calculate the least frequency, that is the natural frequency of the oscillation, that is the fundamental frequency first. So here we can say if frequency is least, the value of m and n should also be least. That means m should be equal to 2 and 2n minus 1 should be equal to 3. Right? That means m value is 2 and here n value should be equal to 2n minus 1 equal to 3. That means 2n equal to 4, that is n equal to 2. It means if we substitute the value of m or n in either of equation, we can get the value of lambda. So let us substitute the value of m in this equation, m equal to 2, that means m equal to 40 centimeter. This 40 centimeter should be equal to the maximum wavelength because it is the least frequency. So maximum wavelength equal to 40 centimeter. Okay, so let us write this ratio and maximum wavelength again to the next page. This is the maximum wavelength. Now let us calculate the velocity of the longitudinal wave in the rod. We can use the formula V equal to under root y divided by rho. So we can substitute the value of y and rho, and this value will be equal to 4000 meter per second because y equal to 144 gigapascal and rho equal to 900 kg per meter cube. So wave velocity is 4000 meter per second, right? Now for the minimum frequency, we know minimum frequency, let us assign this value as f naught. So f naught should be equal to the wave velocity divided by wavelength, that is v divided by lambda naught, and v equal to 4000 and lambda naught equal to 40 centimeter. So we need to change this value in the meter. So this is 4000 divided by 0.4. This is equal to 10,000 hertz. That should be equal to 10 kilohertz. So least frequency of oscillation for this type of the structure equal to 10,000 kilohertz. So here we got the fundamental frequency or minimum frequency of this type of the oscillation. Now let us move to calculate the next higher frequency. So let us write all three equation number 1, 2 and 3, right? Here we can say for the next higher frequency, that will corresponding to the next integer values of small m and n. And here we can observe the ratio is m divided by 2n minus 1 equal to 2 by 3. So the next ratio, if we multiply this ratio by 2 by 2, so this will be equal to 4 by 6. That means m equal to 4 and 2n minus 1 equal to 6. If 2n minus 1 equal to 6, that means 2n equal to 7, n equal to 7 by 2. But m and n both should be integer. That means this ratio is not permitted. So let us multiply this ratio by 3 by 3. If we multiply this ratio by 3 by 3, that means this will become 6 divided by 9. That means small m should be equal to 6 and 2n minus 1 should be equal to 9, right? So let us write this value, and if 2n minus 1 equal to 9, that means 2n equal to 10, that means n equal to 5, right? And we can observe here m and n both are integers. That means this value is permitted. That means for the next higher oscillation, m should be equal to 6 and n should be equal to 5, right? If we substitute the value of m in equation number 1, we can get the wavelength corresponding to the next higher oscillation. So we can use the formula, that is equation number 1, and substitute m equal to 6. So this is equal to 80 divided by 6 centimeter. This is the wavelength. That is equal to 40 divided by 3 centimeter, and this is equal to 4 by 30 meter. Okay. Now for the next higher frequency, we can write frequency, let us assign this value as f1. That is f1 should be equal to v divided by lambda, right? And we know the value of v, we have calculated the value of v, that is equal to 4000 meter per second, and this value is 4000 meter per second, and this value is 4 by 3 meter. So this is equal to 4000 divided by 4 by 30, and this, if we calculate, that will be equal to 330 kilohertz or 30,000, right? So this is 30 kilohertz. Here we can observe the fundamental frequency was 10 kilohertz. Next higher frequency is 30 kilohertz. That means rod is oscillating with the odd harmonics here, right? So here in this case we calculated the both type of the frequency, fundamental and next higher frequencies. Okay. Now let us discuss one more illustration related with the rod clamp at the middle point. So in this illustration it is given a rod of length 1 meter is rigidly clamped at the midpoint. Longitudinal stationary waves are set up in the rod in such a way that there are two nodes on either side of the midpoint. The amplitude of the antinode is 2 into 10 to the minus 6 meter. Write the equation of motion of a point 2 centimeter from the midpoint and those of the constituent waves in the rod. And we are given Young's modulus of elasticity of material of the rod is 2 into 10 to the 11 Newton per meter square, and density equal to 8000 kg per meter cube. Let us place the problem to the next page and try to draw the diagram of the situation. The length of the rod is 1 meter. Middle point is clamp. That means that point, clamp point, should be node. If middle point is clamp, that means the ends of the rod should be free. That means there should be antinode. And between node and antinode, because it is given on either side of the middle point there are two nodes. So here we can make the diagram of situation like this: antinode, antinode, node, and two nodes on either side. Now we can draw the wave structure. Between node and node there will be one loop, and there node and node there is another one loop. and here should be half loop, and similar case for the right hand side also. So the wave structure should be like this. Now we can observe, we know the length of one loop equal to lambda by 2. That means this should be equal to lambda by 4. So here we can write the length of the different loops. This is lambda by 4, lambda by 4. This is lambda by 2. This is also lambda by 2, lambda by 2, and lambda by 2. That means this is lambda plus lambda 2 lambda plus lambda by 2. That is 5 lambda by 2. That 5 lambda by 2 should be equal to L. So let us write the relation for the wavelength, that is L equal to 5 lambda divided by 2. From this relation we can calculate the value of lambda, that is equal to 2L divided by 5, and we know L equal to 1 meter, that is equal to 2 multiplied by 1 divided by 5, that should be equal to 0.4 meter or 40 centimeter. So we got the wavelength for this situation. So in the next page, let us write the wavelength. Here, this is the wavelength. Now let us calculate the velocity of the wave in the rod. Here, velocity of the wave can be written by the formula under root y divided by rho. So velocity of the longitudinal wave should be v equal to under root y divided by rho. And this y, it is 2 into 10 to the power 11, and this rho is equal to 8000. So let us substitute the numerical values here, right? So this after solving should be equal to 10 to the power 4 divided by 2, that equal to 5000 meter per second. This is the velocity of the wave in the rod, right? So let us write the velocity of the wave here, v equal to 5000 meter per second. Now we have the formula for the frequency. We know the frequency should be equal to the wave velocity divided by wavelength. And we know the velocity and wavelength. Velocity is 5000 and wavelength is 0.4 meter. So 5000 divided by 0.4, this should be equal to 12,500 Hertz. This is the frequency of this type of the oscillation. And we know the equation of the stationary wave. In this case, let us assume this point P point as the origin, that is x equal to 0. So if we consider x equal to 0, the equation of our stationary wave should be like this, that is y equal to 2a, and first we should introduce the cos term because here is antinode, we cannot have the displacement factor equal to 0. So the stationary wave equation should be equal to 2a cos 2 pi x divided by lambda multiplied by sine 2 pi n multiplied by t. This is nothing but k 2 pi divided by lambda. So this is 2a cos kx multiplied by sine omega t. Now we know the value of lambda, right? We know the wave velocity also, and we know the frequency also. So we can calculate the value of the frequency, that is 12,500, and we can substitute the value of wavelength, that is equal to 0.4, and here it is given the amplitude of the antinode is 2 into 10 to the power minus 6. That means this amplitude is 2a for the this stationary wave. So this 2a should be equal to 2 into 10 to the power minus 6 meter. So this equation will be like this. Okay, so let us do one thing. Let us write this equation to the next page here. Now let us simplify this equation. We can write this equation, that is 2 pi x divided by 0.4. So this is equal to 5 pi x, and this is equal to 25,000 pi multiplied by t, this one. Okay, now we need to calculate the equation of motion of a point 2 centimeter from the middle point. It is not given, left side or right side. So let us take right side point. Right side point should be equal to, this is the middle point, that is, this is 50 centimeter point, and right side of this 2 centimeter should be equal to 50 plus 2, that should be equal to 52 centimeter, that is equal to 0.52 meter. Now we can substitute the value of x in this equation. By this way we can find the value of equation of motion of point 2 centimeter from the middle point. This is the equation. Okay, now we need to calculate the equation of constituent waves in the rod. So let us do one thing. Let us write this equation in the form of a standard form of the stationary wave, that is y equal to 2a cos kx sin omega t, and this should be equal to this value, right? This value. So let us write this value, this equation, right? And here k equal to 5 pi, and this omega equal to 25,000 pi. So we can observe here this term is the multiplication of the two trigonometrical term, that is the cos 5 pi x multiplied by sine 25,000 pi t. We have trigonometrical formula for this relation. That means if we want to have the constituent wave, we need to convert this multiplication formula into the addition formula. So we have the trigonometrical formula like this. Okay, now here this a is equal to 5 pi x and this b is equal to 25,000 pi t. So now we can substitute the value of k and omega. So equation of the component wave should be equal to y1 should be equal to 1 into 10 to the power minus 6 sine 25,000 pi t plus 5 pi x, right? This is omega t and this is kx. And second constituent equation is equal to y2, and y2 equal to 1 into 10 to the power minus 6 into sine 25,000 pi t minus 5 pi x. So these are the two constituent wave, and we can observe these two waves are moving in the opposite direction, and this value is the amplitude of the progressive wave. This should be equal to half of this value. This value is 2 into 10 to the power minus 6. So this value a should be equal to 1 into 10 to the power minus 6 meter. So these are the constituent wave.